Alright, who's ready to start learning? This video, it's going to be done in a bit of a different format, because this one's going to be done live to demonstrate the power of proof, and that it's really about understanding and not just memorization like formulas are. And understanding is really what we want to get out of math. So let's jump right into the content that I promised you, and that was actually proving statements. So what you want to do is you want to find a statement that is verifiable, and you want to work with it. 3 equals 3, boom. Verifiable, proven statement. Now let's pick a slightly harder statement to prove to really get at what I'm trying to talk about when I talk about a direct proof. Because that was pretty direct right there. 3 equals 3, therefore 3 equals 3. That was fairly direct. Let's look at what happens if we're trying to evaluate if 3 is in the set or collection of numbers, alright? So set of numbers between, and I'm just going to write it down little squiggly brackets, 1 and 10, alright? So that's what we're looking for. We're looking to see if 3 is in there. So one of the ways that we could go about directly proving this is start writing down some of the numbers between 1 and 10. Well, we could do 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, let's get some more room here, 5, 5.5, and you're probably screaming at me, why are you using half intervals, and why did you not stop when you reached 3? You're already thinking about ways to simplify this. Good, keep that in mind. Now, when we're looking at proving this statement, this is one of the easiest ways to go about directly. And let's just list out some elements, see if it's in there. And elements are just a fancy word for saying members of a set, right? And a set's just a collection. So that was one way to go about it. And is there a faster method? Yes, and for that, we're going to need to delve into a little bit of understanding how we prove things. When we prove things, the first thing that we need are axioms / postulates. And these are undeniably true statements. 1 does not equal 0. 2 equals 2. Triangle has 3 sides. These are all just undeniable statements, these axioms / postulates. And you use these true statements through logic to reach what's known as your theorem. And you may have heard of Pythagoras Theorem, which featured a few times in my last video. A squared, b squared, c squared, right? C squared is the sum of a squared and b squared. Now let's look at applying this method to proving the statement that we just finished looking at earlier. So we have our number 3. We want to show that it's in a set of numbers between 1 and 10. Let's see if 3 fits right in there somewhere. One of the ways we could go about proving this is we can assume that 3 is greater than 1. 2, we can assume that 10 is, that is not the way I want to say it, 10 is greater than 3. And finally, we want to say that our set through 10 are all numbers that are greater than 1 and less than 10. And they have to satisfy this rule in order to be included in this set between 1 and 10 right here. That's it. Now that right there is a definition. Not actually an axiom, but a definition of our set. So using those statements, what we're going to notice is that the number 3 satisfies the definition, right? The number 3 is indeed greater than 1, and it's indeed less than 10. And if 3 satisfies those conditions, 3 must underline that a few times, be in the set. 1, 10. So that's one way that we could have sped up the process and go about directly proving it. Now, direct proof doesn't always just concern sets and whatnot and these weird structures you've never seen before in math. So let's look at something that you have seen before. Linear equations. Y equals 1, y equals x. This will be our simple set of linear equations. Now, how do we prove that a solution exists? One of the ways we could go with direct proof is just to solve for it. Well, we know that y equals 1. Substitute in 1 here, and we get x equals 1. Our solution is 1, 1. That is the point that they intersect at. Now, proofs are a little bit flexible with how we can go about them, because we could have proven this in another manner. We could use, all right, as our postulate, we could say that lines are continuous to linear equations, like we saw earlier there, those two examples, are lines. So, in case you're a math person, I don't want you confused when I say linear equations. I'm not talking about proper linear equations, just those examples that we handle with grade 9 math normally. So, linear equations are lines, and 3, we are going to assume that the line y equals 1, constant. So what we're going to do is we're going to look at the point on the second line, y equals x. It contains the point 0, 0, and it contains the point 2, 2. Now, 0 less than 1 and 2 is greater than 1. And if it's continuous, there, the 0 and the 2, right there, it must pass through line y equals 1. And therefore, a solution exists. So whenever you have a statement, there's normally always going to be multiple ways to go about proving it. It's not just cut and dry as I had earlier, where it's just the one method that I showed you. There's always going to be more than one way to show that a statement is true in math. Now, what about when the statements start getting out of hand and quite large and cumbersome to deal with? One of these problems is the four-color theorem. That's if we have a map. I'm just going to put down some lines. So a map is just going to be some borders. Right? This is kind of like a fake country line. And the theorem states, the four-color theorem states that I could color this with 4 colors as long as they only ever touch on a diagonal. The minimum number of colors I need will always be 4. The minimum, well, not the minimum, it's always going to be 4, but the maximum number of colors to do it with, to solve this problem, none of the colors touch on any of the edges, is going to be 4, always on a flat surface. And this problem was not actually solved by a person. It actually ran through just under 2,000 scenarios in 1976. And the proof was by Apple and, oh, I'm blanking on his name right now. Oh, Apple and Hawken. And this was the first computerized proof. And it was actually a little bit of a controversy in math. To most math people, that's a little bit of a surprise. But that was the first computerized proof in math. And that was a direct proof. They went through all the elements like we said earlier. And that was one of the challenges that direct proofs face. Now let's look at something else. What if we have something like the primes? And we visited those briefly last video. The primes, well, let's look at that exact question we had last time. Do they go on forever? 2, 3, 5, 7, 11. They just keep going on. Do they end? Is there an end to this madness? Well, it's a good question. But this time, there's an infinite number of numbers to check. This isn't the same scenario last time where there's 2,000 scenarios to check and they had their proof. What I want you to do is I want you, the viewer, to either A, submit a proof of this, the fact that there's an infinite or finite number of primes in case you find that, or B, submit your grievances. And by grievances, I mean any problems you had with finding the proof itself. Because finding proofs is supposed to be something that's difficult to do. This isn't a mindless task, and I want to get that across, and I really want you to try it, and I want you to share some of your grievances, because I want to show some of the top grievances, and, kudos to you if you do prove it. I want to show that example. Now, this video is coming to an end, and I just want to give you a little hint. Little small hint. And it's going to lead into the next video when I see you hopefully soon enough and not as long as a delay as this one. A little bit busy. Here's your hint. Look for a contradiction. Look for a contradiction when you assume finite primes. So when you assume finite primes, see if there's a contradiction. And try to reason what that contradiction really means. And next week, I'll show you exactly what's going on. But for now, keep on learning. See you next week.